The most important thing to remember is exam 2 is on Monday. And the topics for this is everything. So remember, you have to go all the way back to be ready for everything all the way back to the beginning, and everything up through rigid body kinetics. And today I'm going to finish doing the pulley with mass and size. That's the last topic in this section. I think I'm going to... So you don't have to worry about this for the exam. I'm not going to assign something on this until after the exam. So the stuff I'm doing here, you don't have to understand that for Monday. But there is an assignment question coming on that for after the exam. So eventually you have to do a problem like this. Yeah, that'll be on there. I mean, that's eligible to be on there, right?
Is the weekly 1 and 2 enough practice to cover everything, or do we need to?
Probably not. I haven't even looked at all what topics are on there. It would be better to just glance through all the daily problems and just each one ask yourself if you know the steps to go through it, you know. And when you're a little hazy on it, then go through those problems. And when you know right away, then you can skip those. I think that's the best way to get ready for it. Okay. All right, so let's do this example. And there's one thing I didn't do last time, I'm pretty sure. So this is the pulley with mass and size. And I want to go back and do this problem first for a pulley that doesn't have mass and size, like the ones you've always done up until now, and you'll still usually, this is the way you'll do them. And so we have something to compare to at the end. Okay, so part 1. A massless pulley. By the way, we're still assuming frictionless with everything we're doing, but dealing with friction is really easy. You just add on a friction couple. So what? That's gone. Okay, massless pulley. So anyone in your notes, can you tell me which side? I think it was a 1 kilogram and a 2 kilogram that we did last time. Which side was which? You're backwards from me. 2 is on the left, okay. Stupid OneNote. That just about crashed my internal computer. Instead, it only crashed my external computer. Okay, so like this. So we're going to do this first massless, and then we'll put in the mass. So for this one, we're going to do a free body diagram of each one of these. I'll do the 2 kilogram first. There's a weight force down of 19.62, a cable force up So Newton's second law says 0t plus 0 negative 19.62 is equal to 2 times the acceleration. And we're going to, so all we have to recognize is that this 2 kilogram one is moving along the y-axis, so I'm going to call this 0a. And there's only one useful equation here that says t minus 2a is equal to 19.62. So I'll call that equation star. And now we can do the 1 kilogram. The weight is 9.81. The force up is T, okay? This is, I guess, the fundamental difference between a massless pulley and a pulley where you're dealing with the mass and the size. With a massless pulley, the tension in the cable is the same all the way along its length. The mass in the pulley leads to the two parts of the cable having different tensions. Okay, so for this massless part, both of those two tensions are the same. Newton's second law here says 0t plus 0 negative 9.81. Leave me alone. They're taking back my house. Ah! Mass is 1 kilogram. Now we have to think about how the acceleration of this one relates to the other one. This is a pretty simple relationship. If the 2 kilogram goes up 1 unit, the 1 kilogram goes down 1 unit. And so this is just 0, negative a. And so the only useful equation here says t plus a is equal to 9.81. And now this is a, yep.
If free body one was just magically able to move to the right instead of down for the same forces, how would you write the a part of that?
Okay, so if, right, if instead of hanging like this, one was sliding along a ledge, that's what you mean, right? Horizontally along the ledge. So then you would think, so now one can only move horizontally, and you think, okay, if 2 moves up 1 unit, 1 moves to the right 1 unit, and so that a would be a0. Okay. Was that the question you asked? Okay. So now we have these 2 equations that we have to solve. Pretty easy. I'll use, so I'm going to use the negative of equation 2 star. So we have t minus 2a is equal to 19.62. The second equation I'm going to say is negative t minus a is equal to negative 9.81. And now we can just add these two. That's a linear multiple of these equations. So we have negative 3a is equal to positive 9.81. And that says that a is equal to negative 3.27, I think. Yeah. Okay, so that says that the 2 kilogram, I mean, obviously the 2 kilogram is going to accelerate down. So if you plug this back into the acceleration vector, this thing, for the 2 kilogram, you get 0, negative 3.27, or, you know, it's going down at 3.27. I say it's going down at 3.27. We don't really know whether it's going up or down. I didn't give you enough information. So which direction it's moving is the velocity. This is the acceleration. So if it's going down, it's speeding up at this rate. If it's going up, it's slowing down at this rate. All right, so now part 2. This is what we're going to compare to. So now the pulley has, what did I say in this? I think I probably gave, well, did I give a mass and a radius for this, or did I just use MR? Okay. So we're going to say the pulley has a mass M, a radius R, I'll call it capital R, and a moment of inertia about the center of mass, IC. Otherwise, everything's the same as this picture. I'm going to go through this again. I'll go through what we've done already a little faster, I suppose. But the first thing I'm going to do is isolate the pulley. So a free body diagram of the pulley. And let me be clear about what I'm isolating. So I'm going to I'm going to take the pulley and the cable that goes over the pulley, okay? And so the connection between my free body and the surroundings is cable attached to cable. So it's pretty clear what the direction of that pulling force is. You know, it's just going to be straight down in both of these cases. Okay, so we have a force vector with an unknown direction that's applied by the pin. We have a weight force that's equal to mg. And then we have two different pulling forces from the cable. They're different this time. You know, they were the same in this case because there was no mass and no size for the pulley. But this time there's going to be, I'm going to call this a T2 and this a T1. Okay. And I got so excited to do the free body diagram, I forgot to do the steps in order. But step 1, is there a fixed point? Yes. So the about point is the pin. Step 2, well, now we know the about point is the pin, so we want the moment of inertia about the pin, which is at the center. So the moment of inertia that matters to us is just this IC, this moment of inertia about the center. Okay. Don't do that. Okay, that's fine there. So this is step 3. We have the weight. We have the 3 places where the surroundings make contact with our chosen body. So this is it. Now, step 4 is the table. Our about point is the hinge where the pin is attached. I'll start with that force, R. The vector from the about point to where the force is applied is 0, 0. The force is Rx, Ry. Cross product is 0. Then the weight force, that's at the same location, so the row vector is the same. The force is 0, negative mg. I'm going to replace the m, so I'm going to call, we'll do it all in SI units. So this is negative 9.81 m. Cross product is 0. Then T2, the row vector from the about point to where that force is applied is negative R0. The force is 0, negative T2. And so the cross product is RT2. And then the force T1, the row vector from the red dot, the about point, to where the force is applied is positive R0. The force is 0, negative T1. Cross product is negative RT1. Step 5, this is Newton's second law, only if there's no fixed point. The fact that there's a fixed point means we don't need this. So now we'll go on to step 6. And that says RT2 minus RT1 is equal to our moment of inertia times the angular acceleration. So this gives us our first equation. Let's see, RT1 minus RT2 plus IC alpha is equal to 0. I'm just putting it in that form in case we have to use reduced row echelon form, and I'll call this our equation star. So this is one equation and 3 variables. Any questions about that?
Oh, I have a question.
Yeah.
Wait, if you go back up to the table, how do you know for T2 and T1 if the R is negative or?
Yeah, because the definition of that row vector is from the about point to where the force is applied. So if this T1 is applied over here, that's not T1, T2 is applied over here, then that vector is this.
Oh, which is negative.
Yeah, negative x direction.
Okay.
Exactly. Any other questions? Okay, well, one equation and 3 variables, no matter how good you are at algebra, that ain't gonna work. So what else do we know? So now we're gonna isolate those the two masses. And this, we don't have to use the 6 steps because these, we're not worried about the rotations or anything like that. These are just particles. So free body diagram of, I'll do mass 2 first. No, we know the mass of this. This is 2 kilograms. So the weight force is 19.62. And the cable force is T2. So Newton's second law here says 0 T2 plus 0, negative 19.62 is equal to 2 times the acceleration of this thing. Both of these are going to be moving in the vertical direction. So this is, I'm just going to call this 0a2 for now. We'll think about what these accelerations are in a second. Okay. And so our second equation says T2 minus 2A2 is equal to 19.62. That's equation 2 star. Now we have two equations. And we've added this new variable A2, so we're at 4 variables. So we haven't made any noticeable progress. And now we're going to go to a free body diagram of the 1 kilogram. The weight down is 9.81. The force up is T1. Newton's second law says 0 T1 plus 0 negative 9.81 is equal to the mass times the acceleration 0 A1. And so we get this new equation that says T1 minus A1 is equal to 9.81. That's equation 3 star. And so now we have 3 equations. We added another variable. So now we have 5 variables. And now we need 2 constraint equations. And this is something in the next, when we get into the next topic, which is linkages, motions of collections of rigid bodies, like basically the dynamic version of structures. This is how we're always going to think about it. We're going to get a set of equations and a set of variables from the equations of motion. That's Newton's second law and the moment equation. And then we're going to have to use the geometry to come up with a set of constraint equations to catch the number of equations up to the number of variables. So that's what we have to do now. Anybody have any idea where these constraint equations are going to come from? What can we use here? What do we know about relationships between? So these constraint equations are always just going to be kinematics. We're kind of done talking about the forces and stuff. Yes?
The last equation, that's not to be A1.
Yeah, so we're going to come up with a systematic way to rename A1 and, oh, you're saying this, right? Yes, you're right. Yes. Anybody have, yes?
Watermelon?
Right, exactly. So now what we know is, here are 3 of our equations. The angular acceleration of this body, and the acceleration of the 2 kilogram thing and the acceleration of the 1 kilogram thing. But notice that the accelerations of those masses are the same as the vertical accelerations of these 2 points on the pulley. Okay, so we're going to use the watermelon equation to calculate the vertical components of those accelerations. And then we're going to relate that to the A's. Anybody have any questions about that reasoning?
Are we not able to use A1 equals negative A2 1?
Well, that's what the watermelon equation is going to tell us that. So I think maybe kind of a more systematic way is just to keep thinking about kinematic rules. But yes, you could use that fact instead of using one of the 2 watermelon equations. So now the constraint equations. Okay, so the first one says 0, let's do A1 first, 0 is equal to watermelon equation. So alpha cross R plus omega cross R. And let's think about what these things are. Well, one thing that you could notice here, we don't know what omega is, but we're not concerned about this because we only care about the vertical component of the acceleration. Because these two masses are not going to be, they're not really in circular motion. They just have the same vertical component as the point that they're in contact with on the pulley. Do you see that? You feel that? Does that feel right? Okay, so we're going to skip this part. And so all we need are alpha and R. So alpha is just 0, 0 alpha from our variable. And R, I'm doing this for body 1. So what's the definition of the R vector? That, you know, I keep saying keep these definitions in your head. It'll get confusing if you don't have these definitions in your head. Don't try to do this just by like what feels right, looks right, you know what I mean? So the R vector in the watermelon equation is from the center of the circular spherical motion to the point you care about. So that is R, positive R, 0, 0. Okay?
If body 1 is the point, not the mass, is 1.
Body 1,
You said R for body 1.
oh, the 1 kilogram mass.
Oh.
Yeah. So this is the 1 kilogram mass. Okay, so we have that 0, A1, 0 is equal to 0, 0 alpha crossed with R, 0, 0. And so that is 0, positive R alpha, 0. And so our fourth equation says A1 minus R alpha is equal to 0. That is our equation 4 star. This time, now we are making progress. This is an equation that doesn't introduce any new variables. Okay, so now we have 4 equations for 5 variables. And once we do this again for the 2 kilogram mass, we'll have 5 and 5 and we can solve it. So now we have the equation that says 0, A2, 0 is equal to alpha cross R plus omega cross quantity omega cross r. We want the vertical only. Alpha it's still the same body. It's still the same rigid body. So this is 0, 0, alpha. And r is now a vector in the opposite direction from the center of the circular motion to where that cable tension T2 acts. So this is negative r, 0, 0. And so 0, A2, 0 is equal to 0, 0, alpha crossed with negative r, 0, 0. And you get 0, negative r, alpha, 0. And so our fifth equation says A2 plus R alpha is equal to 0. That's equation 5 star. And now we're ready to solve this system. And Chase, that's these two constraint equations, notice, tell us what you said, you know, that A1 and A2 have to be equal to each other. It tells us one other thing too, though. It tells us how they relate to alpha. Okay, so now we can plug this stuff in. I'm going to write this as a new system just of 3 equations. Well, what do we want? We just want that to compare to the case where we didn't have size and mass. I just gave the acceleration vector of A2. So let's see. So I'm going to write this as a system of 3 equations for 3 variables, and I'm going to call my A2, I'm going to call that A. Okay? All right, so my first equation, so A2, anytime we see an alpha, here it is. Anytime we see an alpha, we're going to call that negative A over R. From equation 5 star. Are you with me on that? All I'm doing is solving this system of equations. I mean, you could solve it your own way. I think sometimes it's more confusing watching someone else solve a system of equations because you just want to do it your way. But I'm going to, any alpha I see, I'm going to call negative A over R. And any A1 I see, I'm going to call negative A. And so let's write this stuff out. So we have RT1 minus RT2 minus ICA over R equals 0. So that's our equation 1 star. The second equation, T2 minus 2A equals 19.62. That's equation 2 star. And equation 3 star, T1 plus A is equal to 9.81. And now our only variables are T1, T2, and A. So let's say this is 3 star. So I'm going to say T1 is equal to negative A plus 9.81. And so I'll rewrite equations 1 and 2. You know, this is from 3 star. And so we have R times the quantity negative A plus 9.81 minus RT1.
Isn't it minus RT2?
Yes. Thank you. Minus RT2 minus ICA over R is equal to 0. And the second one says T2 minus 2A is equal to 19.62. So this is our new system with only 2 equations and 2 variables. And now I'm going to use the fact that T2 is equal to 2A plus 19.62. And so we have R, I guess I'll multiply this through, so negative RA plus 9.81 R minus R times the quantity 2A plus 19.62 minus ICA over R is equal to 0. That's one equation for one variable. And so, let's see. We have negative RA plus 9.81 R minus 2RA minus 19.62 R minus ICA over R equals 0. The only variable left is A. So we can group these. We have negative R minus 2R minus IC over R times A is equal to 9.81 R. We have, if you add these two R terms together, you get positive 9.81, you get negative 9.81, then bring it to the other side, so it's positive, right? And so this says,
You're missing a negative by your birds are. Hold on.
this one here, the 9.81.
Hold on. By the circle, yeah, opposite side of the dot, the dates.
Can you come point to it?
That's negative 3R.
Oh, yeah. Okay, right. I tried to pull that negative out and I messed that up. Stupid computer. Okay, so let me get this out of here. And this is, okay, so we have negative, and then this is 3R plus IC over R times A is equal to 9.81 R. And I'm going to divide everything by R. So we get negative 3 plus IC over R squared is equal to 9.81. And so A, this is just making it uglier. Why don't we multiply everything by R? And so we get negative 3R squared plus IC times A is equal to 9.81 R squared. And so A is equal to 9.81 R squared negative divided by 3R squared plus IC. And I think that's it. Okay, so what does this say? So if IC is equal to 0, like in the case where the pulley is massless, then the R squareds cancel out, and we get an acceleration of the 2 kilogram thing downwards at 3.27. Okay?
Like the sixth step, I think I got negative RT1 plus RT2.
Oh no, that would be a frickin' catastrophe. Way back here?
Right there. The RT1 minus RT2. Oh. Okay, no, I'm wrong here.
Okay, this should be negative though.
I think you just lowered with the right.
No, you
So
swapped
it's
1 and
different.
2 there.
Oh, I see. I gotcha. Okay, I was smarter before. I'm only getting dumber now as I get older.
It's only been 30 minutes.
What?
It's only been 30 minutes.
Yeah, that's how fast it's going. Okay, so if IC is equal to 0, that's the massless case. It reduces to our previous result. If IC is not equal to 0, that means the pulley has mass. Then increasing I reduces the acceleration. Okay, so let's plug in a number and see, something that seems reasonable. Let's say that this pulley, the full diameter of the pulley is 0.1 meters, 10 centimeters across. And let's say the mass is 50 grams. So 0.05 kilograms. Okay, how much would that reduce this? This is 50 grams. So then the acceleration of the 2 kilogram, it's going to be in the negative y direction, and it's equal to 9.81 times 0.05 squared divided by the quantity 3 times 0.05 squared plus the moment of inertia is 1/2 times the mass, if we're assuming this is a disk, times the radius squared. Oh, these are all 0.05.
So one.